So now we're going to take a look at IPv6 and how DHCP works in that environment. So I was trying to do this one over, but how a client obtains an IP6 GUA depends on settings in the message. So you have certain flags. Your A flag stands for the address auto configuration flag, and it signifies to use the stateless address auto configuration SLAAC to gain your IP6 information. Your O flag is the other configuration flag, and that signifies that additional information is available from a stateless server. Excuse me. Your M flag is the managed address configuration flag, and that signifies that you're going to get all of your information from the server itself. So, in paying attention to your ones and zeros and the flags in this example, in the first circumstance, my flag A is set to 1, so I'm using SLAAC. In the second example, my A and my O is set to 1, so I am using SLAAC and my DHCP6 server. And lastly, only my M flag is set to 1, so I am only using the server. Using different combinations of the A, O, and M flags will allow your RA messages to inform the hosts about how exactly their options are available, or what options are available, and how they are going to gain their IP6 configuration information. Now, in viewing SLAAC, not every network has access to a DHCP-v6 server, but every device in an IPv6 network needs a GUA. So SLAAC is the stateless address auto configuration method that enables your host to create their own unique global unicast address without the services of a server. SLAAC is a stateless service, which means that there is no server involved in the communication. There is no server that would maintain network address information to know which IP addresses are being used and which ones are available. SLAAC sends periodic RA messages every 200 seconds, providing addressing and other configuration information for hosts to auto-configure their IPv6 addresses based on that RA. A host can also send a router solicitation message requesting an RA be sent to them. So SLAAC can be deployed as SLAAC only or SLAAC with DHCP. So R1 in this example, G001, has been configured with the indicated IPv6 GUA and link local addresses. Remembering, going back, your link local address starts with FE80. So the addresses are link local FE80:1, the global unicast address, which I'm not going to read to you, and don't forget your multicast groups. So this interface belongs to the all nodes group of FF02:1. R1 is configured to join the all IPv6 multicast group and start sending RA messages containing address configuration information to the hosts utilizing SLAAC. Again, in order to put this in place, first thing you need to do on R1 is to configure IPv6 unicast routing. Okay? You have to tell the router to act as a SLAAC server. Again, I'm using the word server, but it's not an actual server, so I hope you do understand that. But in order for that router to send out those periodic messages, those RAs, you have to tell it, hey, you're going to send out this RA message every 200 seconds to inform your end host what they're supposed to do in order to configure themselves. So the IPv6 All Routers group responds to the IPv6 multicast address of FF02:2. The show IPv6 interface command will verify that R1 has certainly joined that group. So now R1 joining that group, as you see here, will now begin to send RA messages every 200 seconds to all nodes that are in the IPv6 arena. Now, RA messages from R1 have the following flags set. A is set to 1. This is going to inform the client to use the IPv6 GUA prefix in the RA and then dynamically create its own interface ID. The O and the M are both set to 0, which informs the client to also use the additional information in the RA message, such as DNS server, MTU, and default gateway information. You want to verify with the ipconfig Windows command and confirm that PC1 has generated its own IPv6 address. The default gateway address is the link local address of R1001, as you see up here. Now, a router sends RA messages again every 200 seconds or when it receives a request from a host. So a host doesn't necessarily have to wait until the next round goes out. It can request information in the interim of those 200-second messages. IPv6 enabled hosts wishing to obtain addressing will send a router solicitation to the All Routers multicast address of FF02:2. So in this example, PC1 has just booted and sends an RS message to the IPv6 All Routers multicast address of FF02:2, requesting information. R1 generates an RA and then sends the RA message to the IPv6 All Nodes multicast group of FF02:1 in response to the request. PC1 will then use this information to create its own GUA. While using SLAAC, a host acquires its 64-bit IPv6 subnet information from the router's advertisement and must generate the remaining 64 interface identifier, either using, again, the randomly generated or the EUI64 that we've spoken about before. Within the randomly generated, the 64-bit interface ID is randomly generated by the client's operating system. This is the method now used by Windows. EUI64, the host creates an ID using its 48-bit MAC address. It then inserts the hex value of FFFE in the middle of the address and then flips the 7th bit. Some operating systems default to the randomly generated instead of the EUI64 due to privacy concerns. So this is because the Ethernet MAC address of the host is used by the EUI64. So if you know how to reverse the process, then you can grab somebody's MAC address and then do some really awful things with it. So Windows, Linux, and Mac OS allow for the user to modify the generation of the interface ID to be either randomly generated or to use EUI64. Now, a SLAAC host may use the following duplicate address detection process to ensure that the GUA is unique. The host will send a neighbor solicitation message with a specifically constructed solicited node multicast address containing the last 24 bits of the IPv6 address of the host. If no other device responds with a neighbor advertisement message, then that address is virtually guaranteed to be unique and the host will use it. If, however, an NA is received by another host, then the address is not unique and the host must generate a new interface ID to use. Now, in reality, data is really not required because of a 64-bit interface ID, which provides 18 quintillion possibilities. Therefore, the chance of a duplicate address is remote. However, the IETF recommends that DAD is used. Therefore, most operating systems will perform DAD on all IPv6 unicast addresses, regardless of how the address was configured. Now, within your stateful DHCP, it does not require SLAAC, while stateless DHCP does. So regardless, when an RA indicates to use DHCP-v6 or stateful DHCP-v6, the host sends an RA message, a router solicitation. So the router responds with an RA, a router advertisement. The host sends a DHCP-v6 solicit message. So the process is the same in gaining information from a server. The names are just different. So in IPv6, it's solicit. You're soliciting for information. The server will then respond with an advertised message. The host will then respond to the DHCP server, where the server will then send a reply with the designated information. Server to client DHCP messages use UDP destination port 546, while client to server will use 547. Now within stateless, if an RA indicates that stateless is the method to be used, the host uses the information in that message for addressing and then contacts the server for additional information. The DHCP server only provides configuration parameters for clients and does not maintain a list of bindings because it is stateless. So, as an example, PC1 receives a stateless RA message containing the IPv6 GUA network prefix and prefix length. The A flag is set to 1, informing the host to use SLAAC. The O flag is set to 1, informing the host to seek all other information from the server. The M flag would be set to 0. PC1 sends out a solicit message seeking additional information from a server. Stateless is enabled using the IPv6 ND other config flag interface command and by setting the the O flag to 1. So the highlighted output confirms that the RA will tell the receiving host to use a stateless auto configuration because the A flag is set to 1 and to contact a DHCP server because the O flag is set to 1. You can use the no IPv6 ND other config to reset the interface to the default of SLAAC only. Excuse me. Within stateful, the host contacts the server for all of its information. The server is stateful and maintains a list of those bindings. Now in this example, PC1 receives a stateful RA message containing the IPv6 GUA network prefix and prefix length. The A flag would be set to 0, informing the host to contact a server. The O flag would be set to 0, also informing the host to contact a server. The M flag would be set to 1, which states use the server for everything. So PC1 then sends a solicit message seeking additional information from a stateful server. So stateful configuration is done by this, IPv6 ND managed config flag interface, and by setting M to 1. So the highlighted output in the example confirms again that the RA will tell the host to obtain all IPv6 configuration information from the server because the M flag is set to 1. So when you do these commands, like in this case, the IPv6 ND managed config flag, it automatically will set the M to 1 by the nature of that command. So Cisco iOS routers are powerful devices. In smaller networks, you do not have to have separate devices to have a DHCP server, client, or a relay agent. A Cisco router can be configured to provide those services. Specifically, it can be configured to do one of the following. DHCP server, where the router would provide stateless or stateful services. A client, where the router's interface would acquire an IPv6 IP configuration from the server. Or a relay agent, where the router would provide forwarding services when the client and the server are located on different networks. So the stateless DHCP server option requires that the router advertise the IPv6 network addressing information in the RA message. There are 5 steps to configure and verify a router as a stateless DHCP server. First thing again you do, enable unicast routing with the IPv6 unicast routing command. Then you need to define your pool. So slight difference from IP4, it's just IPv6 DHCP pool. And again, that pool name has to be precise. Configure your options for the pool. You configure your DNS server and your domain name. You bind the interface to the pool with the IPv6 DHCP server pool name. So again, remembering, these two have to match. Whatever you put here has to match whatever you put here, or DHCP will not function. So case sensitivity is important. Then you manually change the O flag from 0 to 1 using the IPv6 ND other config flag. Then RA messages sent on this interface will indicate that additional information is available from a stateless server. The A flag is one by default, telling your clients to use SLAAC to create their own GUA. Once you do all this, again, always verify. Don't immediately go to a ping. Okay, a lot of you in the lab automatically go to a ping, and then you're confused as to why your ping doesn't work, and then you call me over, when in reality you should be troubleshooting why your ping doesn't work. Okay? So, always do an ipconfig /all to make sure an address is obtained before you do any testing on your networks. A router can also be a client and get information from a server. So again, enabling my unicast routing, configure the client router to create an LLA by activating it. An IP6 link local address is created on a router when a global unicast address is configured or without a GUA using the IPv6 enable interface command. Cisco iOS uses EUI64 to create the remaining interface ID. Configure the client router to use SLAAC using the IPv6 address autoconfig command. Verify that the client router is assigned a GUA with the show IPv6 interface brief command. Verify that the client router received other necessary DHCP information with ipconfig /all is the easiest. And then show IPv6 DHCP interface G001 to confirm that DHCP option information such as your DNS server, domain name, have all been received by the client. Now, your stateful option requires that an IPv6 enabled router tells the host to contact the server. So configurations there, again, unicast routing, creating my pool. Common options are including the address prefix command, the domain name, DHS server IP address, and more. You bind it to the pool. You manually change the M flag from 0 to 1 using the IPv6 ND managed config flag. You manually change the A flag from 1 to 0 using the IPv6 ND prefix default no autoconfig interface, which informs the client not to use SLAAC to create a GUA. The router will now respond to stateful DHCP requests with the information contained in the pool. Again, verifying at the end with your ipconfig/all. A router can also be a client. The client router needs to have IPv6 unicast routing enabled. After that, you configure the client router to create an LLA. You configure the client router to create, an IPv6 link local address is created again when a global unicast address is configured or without a GUA using the IPv6 enable. Cisco uses EUI64 to create the remainder of the ID. Then you're going to configure the client router to use DHCP with the IPv6 address DHCP interface command. Verify it with your show brief. Verify that the client received other information using the show IPv6 DHCP interface G001 command. So in verifying your pool, use the show IPv6 DHCP pool command to verify the name. So here I'm identified as an IPv6 stateful. Address allocation prefix here is the network associated with. Currently there are 2 in use. Other information is the DNS server as well as the domain name. And again, currently there are 2 active clients. Show my bindings. Use the binding command to display the IPv6 link local address of the client and the global unicast address assigned by the server. This information is maintained by a stateful server only. It is not maintained by a stateless. So here, show my bindings. I see my client link local address. I know this because it is FE80. I see my GUA because it starts with 2001. Okay, so this is your binding of your link local address to your GUA. Now a DHCP server, again, if it is located on a different network, then it has to do a relay. So this command is configured on the interface. So just like you saw in DHCP4, if your server is a different router or on a different LAN than the requesting client, there has to be a relay set up. If there is not a relay set up, then you do not gain addressing information. So this command is configured on the interface facing the DHCP server. So here from LAN 1 on my left, G001 is the interface that is facing toward the server. R1 becomes my relay agent. So the command goes on G001, and the command is IPv6 DHCP relay destination, and then the actual destination IP address of the router that is holding, in this example, the server information. Verify the DHCP relay agent is operational with the show IPv6 DHCP interface command and the show IPv6 DHCP bindings command. So here on the left, you see R1 is showing that G001 is definitely in relay mode. You also want to verify within Windows that your device did grab the appropriate addresses. So that is your perspective from a DHCV6 server.